chance to sort of revisit these ideas of looking at the construction of logics through the lenses of this judgmental use. And it will also give us an idea how we can define sort of the very Howard correspondence to it. And so I will touch a little bit on like what kind of systems we can model if you think about it from a substructural point of view. Now, what does substructural mean? Yes? You remove a structural rule. Exactly. Okay. So essentially we can remove, or the minus here, you can remove weakening, which essentially weakening said some additional assumptions don't do any harm. So in the substructural setting, if you have leftover assumptions, they do harm. Okay, so general weakening, you can think of saying additional assumptions don't harm. And did you mention a second rule? Contraction. Which essentially says that we can use assumptions as often as we like.
Mentioned the system too, but I don't know if that's just wrong.
That's so wrong.
Okay.
So reuse. So we can get different logic laws depending on how we play with them. Okay, so sometimes writing just W for weakening and contraction. I'm writing sometimes C. There is a third structural rule that we sort of taken for granted when I was talking about logic, which was the fact that the order of our assumptions didn't matter. And you might recall that when Anya was talking about dependent type systems, she was actually saying, well, the order does matter because we have dependencies among them. But I will not really talk about exchange. Exchange is sort of the third structural property you might want to consider. Yeah.
What about the associativity of assumptions? Because right now we just assume that they're like one after the other, but if we thought of the joining between them as like an operator, we could make it associative.
Okay, so there are two things here. So the Ricardo, yeah. So they asked this question: is there an associativity operation among the assumptions? And maybe we could define sort of when we add or combine assumptions a bit more formally. I will do that today. So we'll define that a bit more formally today. And then this operation would have certain properties and associativity. But exchange is sort of a more general property because it sort of says you can permute any of the assumptions in any given order. But if you would omit exchange, then you would have essentially an order context. And even in the propositional case, this might be interesting if you want to model a stack, for example. But as I said, I don't want to really talk about ordered logic. I'm going to talk more about lines that omit or admit weakening and or contraction. So intuitionistic logic has both weakening and contraction. So that I sometimes will call it structural logic. Weakening and contraction. Linear has none of the above. Has neither weakening nor contraction. Affine allows contraction, okay, but allows weakening but not contraction. And relevant logic would allow contraction but not weakening. So why would I want to have a logic where I control the usage of these assumptions? And I want to give a slogan for today. So the slogan for today is truth. Truth is ephemeral. It's a fleeting notion. All right, so why would we want to think about assumptions as something that is ephemeral, that might disappear? And a good example is if you think about assumptions, or you want to describe this idea of affordability. So here's an idea. So we're cheap, okay? So tea costs $1. So I'm going to say that $1 implies that I will get tea. And coffee costs $2, so I must have $1 and another $1. And now I want to prove that with $1 I can buy a coffee. Now this should, if I think of real money, this should not be possible. Unless I'm a forger and I can clone money, okay? Or I can print money. Intuitively, this should not be possible. But in the logic we have, we can simply do this in structural logic. We use implication in production, and that introduces our assumption that we have $1, and we need to prove that we can get coffee. And in our signature, we have here these two laws, and this law tells us something about coffee. So we say, yes, if I have $1 and $1, I can get some coffee. So I need to prove that I can achieve $1 and $1. And now where it's purple, things go a little bit wrong in some sense, because I can use this assumption to prove that I have $1, and I can reuse the assumption to prove that I have $1. And then I have effectively proven that with $1 I can get coffee. Now, that shouldn't be in some sense the case. Okay? So if you like to model this in a traditional logic, intuitionistic or in classical logic, you would need to somehow be more careful in how you specify these rules. You would need to somehow have maybe some counting of the money you have, and you might need to have some kind of subtraction operation or something like that. Right? That keeps track that something gets smaller. And that's kind of complicated. So the idea of actually tweaking our structural rules and not allowing us to reuse this assumption in both of these branches is a very elegant and direct way of dealing with this problem, right? That we have assumptions that we want to sort of use up, and once they're used up, we can't use them anymore. So what I want to do is I want to revisit our rules that we've seen before under the lenses of linear logic, which essentially omit weakening and contraction. And maybe as an analogy, okay, if you have a linear logic, if you have money, it means you have to spend all your money because you cannot have any money left over. You don't have weakening. Okay. Means really you have $5, you have to spend it. Okay. That means you have to, for example, buy 5 teas, okay, or you have to buy 2 coffees and 1 tea, okay, but you have to spend it all until you have no money left. If you have affine logic, you can be a bit more money conscious. Okay? So you can, if you have $5, you can buy the coffee, and then you still have $3 left, and that's okay. You didn't use the other. So we'll look at linear logic first, and then we'll try to combine it with our original logic, which is structural, and see how we can combine it. And then, hopefully there's a bit of time, then I'll show you how to sort of come up with a logic that rules them all, okay? And binds them all and rules them all, and that will be then a framework called agile logic. And I'll give you at least sort of the idea of what the idea is. Okay, that's the task. Ambitious, but we'll get there. So let's look at Nash reduction, in particular through the lenses of linearity. So the simplest rule we in some sense have in our Nash reduction system are saying I have some assumptions and I can establish something from it. So we're going to have a judgment that will say delta, okay, those will be my assumptions. And I want to prove that A is true. Okay, and I want to establish that A is true under assumptions that each of one is true, but they're ephemeral. So I want to basically say when I use one, then it's gone. Okay? And I must use all of them. So under what conditions? So let's start with variables. Okay? So I have, how can I prove A? Under what assumptions can I prove A? Okay, so the simplest rule, we usually say, oh well, if I have in my list of assumptions an assumption that says A is true, then I can prove A true. That was a rule we've seen so far in the last few days. But now I'm saying I cannot have anything left over, right? So previously it was sort of saying, I have here some delta, and in delta there was this assumption, A true, somewhere in delta. But that allows for delta to have other things in it than X, right? So I'm going to change that. And essentially the only thing I can have on the left is this assumption that X that A is true. Right? Because I don't allow weakening, there cannot be anything else present at this point. Okay. So let's look at implications. Okay, so implications in linear logic, we often write with a lolly. Okay? This is like a bar with a circle on the right-hand side. Looks a bit like a lolly. Okay? So we often pronounce it as lolly, or linearly implies. And the introduction rule doesn't look very surprising. You have some assumptions. You need to prove A log B is true, so A linearly implies B. And what does your gut say? What's in your premise? What does your gut tell you? Extend by A. No? Exactly. So we extend it by A. And it would be a string. So this is going to be our lolly introduction rule. Very good. And now our implication rule is like modus ponens, just as before, except that we now call this lolly. And so if you have A implies B, linearly implied A, then we can be able to conclude B. But we need to now worry a little bit more about the assumptions that we have used, because we want to use them only once. And that means we will have some assumptions that we're using to establish the left premise, namely A implying B. And we'll have some assumptions over here that are used to establish A. And that means the combined use of these assumptions can be used to achieve B. So I wrote here a semicolon. If you want to read it from the bottom to the top, it means you have a set of assumptions, and now you need to split them. You distribute some to the left premise and some to the right premise. Or if you want to think of this as a join, then you basically combine, but it needs to be sort of a join where the assumption should not be present, it should not be present twice in both branches. So as Ricardo was mentioning, right, is this operation then really associative? And it is. You can define it to be associative. You can think of it as a merge. Okay? And if I want to define that operation, maybe I'll do that. How would I define this? So you have here one list of assumptions, and you have here an x that is a true. Okay. And you want to combine this with delta 2. Well, then you have combine delta 1 and delta 2, and then you add an x. Okay, and this is provided that if actually x is not in delta 2, so we do assume that the label on these assumptions is unique. And there's a dual one, here that will say delta 1 joined with delta 2 x a true. We'll combine them. Okay, again, if x is not in delta 1. And then you have rules basically that allow you to combine it with the empty context, and we'll get the delta, and you have then empty delta. Also delta. Yeah?
Potentially make a delta sub 1, sub 1, sub 2, and sub 1 as disjoint union.
Yeah, just join there, it'll be fine.
So what exactly does if x is not in delta 2 union do? Is it that this operation is undefined?
Yes, it would fail. It would be fail. Not only undefined, it would be completely wrong.
Well, what does failure mean?
It means there's no proof.
Okay.
Yeah.
By x not in, does that mean like any other proof of A, or exactly?
No, it means that there's no assumption in delta 2 with the name x.
With the name, okay, yeah.
And names, we're going to keep names unique. You cannot just rename them. Yeah?
I have an observation, but with this, I look at it as splitting.
Yeah, the name is fine.
That makes proofs get really hairy, right? Because, like, if you have some assumption here, but you want it to go there, you have to do like a bunch of exchanges, right?
Right, so I mean, we do, so there are two issues essentially when you come to substructural logic. One is, how do you manage the scope of things? So we still have here the scope of X. So that is a problem we had before, okay, in a structural setting, but it persists here, and in some sense it might get worse. And the reason why it gets worse, it has to do with this splitting operation, because we need, if you think of proof construction, you need to anticipate how you do the split. And so people have designed various kinds of algorithmic solutions to this. You could say I pass everything to the left premise, and then eventually I get my rest of the assumptions out. So here, for example, I might have some additional assumptions, but this is sort of what I'm returning here as a result, because they're still unused. Okay. There are other approaches to this as well, where you basically would label assumptions as being used or unused. So think of this as a resource vector. And essentially you keep always your list of assumptions intact. You don't really split. Keep them all intact, but you keep sort of tags on them. And so in here, this tag essentially is the only one that says I'm alive, okay? And the other ones are all dead in some sense. So when you come to combine it, you do sort of a bitwise addition almost, right? You have a dead assumption, so 0, and one that is alive, so it's 1, so that's okay. 0, 0, that remains dead. Okay. 1, 1 is not defined. So that would be sort of imposing a certain algebra on the usage of these assumptions. And that has many advantages in many ways. And you have to answer these questions if you want to implement it or if you want to actually mechanize these kinds of systems, or if you want to actually prove properties about them, right? You want to prove consistency, normalization, type preservation, subject reduction, whatever your favorite meta-theoretic properties are. For now, I'm giving a very declarative description of the system. But you can derive an algorithm. Yes?
Yeah, I think I'm having a hard time understanding what, on the right-hand side, what the semicolon and comma are.
Okay, the comma is like a cons.
Yeah.
The semicolon is like a join. It's a join, or a disjoint union. Because it's taken two different kinds of context. So this is defining the operation. Going one context with another, using the context. Sometimes people write bow tie, or some kind of other operator, but semicolon is pretty common. Very often people don't define it formally, they just say split. Such that these are disjoint. Same thing with like exchange, like we take exchange sort of in some sense for granted. Yeah.
But the semicolon is meant not theoretic operation, like it's
It's
not simple, it's.
That's right, that's an operation I'm defining here. The comma is part of my grammar. Yeah?
But it seems like the only real thing about trying to introduce something without anything else is turn X of A being true derives A being true. But do we, like if that's introducing, is that introducing something that needs an X? So something else that we use for other rules?
Are we talking about the variable rule? Are you talking about this one?
Yeah, like will we get any more introductions to this? Is this enough to start using it with other rules?
This is enough.
Okay.
Yeah.
How would you go about can you maybe do like a tiny example?
I'll do a tiny example when I talk about the conjunctions, because right now the only example I can do is A implies A. That's a tiny example, but not very interesting. Is that okay?
Yeah.
I mean, I can do an detour example too, like I could, and let's do conjunctions first. A little bit more interesting. One of these I can do it. Just doesn't fine. Oh yeah, okay. That implies that works too. So here's an example. So let's say I have an assumption y that says A implies A. I'm going to drop the true, okay, because I don't have enough space on the board. That means I can prove A implies A. Yeah, so let's call it y. Okay. Let's say I have another assumption here. So x A proves A. That's my assumption x. Yeah. So that means I can prove A. Okay, I can prove A by the elimination rule. fraction over x. Okay, so I'm going to get y a implies a all the a. Yeah, because I'm moving this over here, the implication. Call this lobby. The implication introduction rule. And then I'm going to do another abstraction. So when I prove a with a, so maybe I should have called this b. Okay, maybe it's nicer. Which is another introduction. So let me do this a little bit nicer. Let's say we prove here a implies b. Okay. I have it here b. And okay, take your b, take your a. Okay. Here you get a b. Then you get a over b. And you get b. And that means proven that if you intuitively, if you have a function from a to b, you have an a. Yeah?
And then with this sort of style, are all of your kind of conclusions going in?
Yeah, it doesn't say.
Is that kind of like the goal of this?
We always start with the empty ones when we prove something. Right?
Okay.
When you type check your program, you always start with the empty one. So this is the same thing, you start with no assumption. Okay, yeah?
That's kind of like just kind of unique thing. Does it kind of mean like if one of those contexts like had with like an x and a y, you would be able to combine them?
You cannot combine them. Okay. That's the point. Here you split. And you cannot move the x over here. So you cannot use it over here.
Okay.
So you literally have to distribute one here and the other one over there. I could have solved these premises. Okay, this is the order of these is not important. But could equally construct a proof that says a, probably a, probably b. That would give me a different order here, but that's not important. Yeah. Are we good? All right. Okay. So implications are interesting, but conjunction is more interesting. And so how should we read conjunction? Okay, so previously it says A and B. In order to prove A and B, we need to have a proof of A and we need to have a proof of B. But in the linear setting, it's not so clear what this means. And in fact, there are sort of two readings of conjunctions. One essentially thinks of it as what you can think of as an eager pair. I have essentially resources, where I use some resources to establish A. Okay, and I have some resources I'm using to establish B. That means I can now establish some A and B under the joint set of resources. Delta 1, delta 2. And now the question is, what kind of symbol should I write here? And this is often called a tensor. So this is one form of a conjunction. It basically says, I have resources to achieve A and B at the same time, simultaneously. Okay. So I can achieve. resources to achieve A and B at the same time. Okay. Because I'm using some of my resources to achieve A and some of them to achieve B. So indeed, I can achieve them at the same time. And so this is often related to an eager pair, because when you, the elimination rule, okay, so this proof term for it would be a pair, because the elimination rule now will say, I have used some resources to achieve answer B. Now, I can't just say, I'm going to get the A out, because then I have some resources that I have spent on B, but I haven't used. So that isn't a good way of defining, in this case, the elimination form of tensor. But the way we are defining it is more like a let elimination form, where you can then say, well, if I have such a pair, I have two parts. I have some x, that says A is true. I have some y, which says B is true. And that allows me to prove that C is true. And now I have, under the assumptions that I have delta 1 joined with delta 2, I will have achievements. So if you think of this computationally, it means you have some proof term for a pair. And then you have here essentially a way of getting your hands on both parts of the pair. Okay? You're pattern matching on this pair. You get the left side and the right side at the same time. Okay? So computationally, you must have computed that pair fully. And I call by value semantics, that will mean you have computed both sides of the pair to a value. Okay? And in that sense, you were eager. Okay? You were eagerly evaluating both sides of the pair, because here we were pattern matching in some sense on the structure of this pair, and you have a handle on both sides of this pair. So it's very different from projections, because for projections, it's more like a lazy pair. If you know it's a pair,